This is lesson number 7 for engineering dynamics. In this tutorial we will look at Newton's second law. The tutorial contents includes an introduction to Newton's second law and the types of forces. We will look at some applications with Newton's second law, and we will complete 6 example problems. In the previous 6 tutorials we were looking at the geometrical aspects of motion of the particle. Now we are looking at kinetics of the particle, so that means we are going to be introducing mass onto the particle. In the previous tutorials for the kinematics of a particle, the particle had no mass. Now we're going to introduce mass, which brings us onto kinetics of a particle. So the particle is here, and the particle now has mass. So we show that by this m symbol here, which means a certain mass of the particle. And this particle is capable of moving inside this rectangular coordinate system here, with the two axes x and y. And there's a new parameter called a force now introduced, which acts to cause and impede motion. So Newton's second law says that the sum of all forces acting on an object is proportional to its acceleration by the mass of the object. And it's also important to know that force is a vector quantity, since there is direction and magnitude. So if we apply a force onto this particle with mass m, what's going to happen is that is going to accelerate in the direction that the force is being applied. So it's going to accelerate to the right, because the force here is being applied to the right. Okay, so a force acting on that mass is going to cause it to accelerate in the direction that the force is being applied. So Newton's second law is F equals ma, where we say the force subscript x. So we're just being more specific here, saying that the force in the x direction equals the mass of the particle multiplied by the acceleration of the particle, again in the x direction. So these arrows on top of F here and A there is just telling us that F, the force, and the acceleration A are vector quantities, meaning they have direction and magnitude. Okay, so mass is a scalar quantity, and that is measured in kilograms. The acceleration, as we already know, is meters per second squared, so the units for acceleration is meters per second squared. So that would mean that the units for force would be kilogram meters per second squared. So we just multiply these units together to get the units for force. Okay, and that is kilogram meters per second squared. And we say 1 kilogram meters per second squared equals 1 Newton. And we use this N here, this capital N in italics, to tell us 1 Newton. So let's say if we have two forces acting on this mass, so the strength of those forces is shown by the length of the arrow. So the longer the length is, the stronger the force. And this yellow line here is telling us the direction they will be moving in. Okay, so this is due to the net force causing this mass to accelerate in the direction of the net force. If a net external force acts on the particle, it accelerates in the direction of that net force. The direction of the acceleration is the same as the net force. The mass of the body times the acceleration vector of the body equals the net force vector. So the way we would get the net force would be to just subtract this force from this force, and that would give us the net force. So we would write that like this. Okay, so F1 minus F2 will give us mass times the acceleration. So this here, F1 minus F2, would be the net force, and the acceleration would be this acceleration here. So we could write that like this as well, where we just say the sum of the forces equals mass times acceleration, where the sum of the forces is just adding the two forces, and because this one is negative, we'd get a negative there. So this is just another way of rewriting this side here. We can also write the net force, so F subscript net just means the net force equals mass times acceleration. So these are just different ways of writing it out. And the net force is shown by this yellow arrow here. So let's say if we now have multiple forces acting on the mass, okay, so we've got F1, F2 and F3. If we added all these forces together, that is going to produce a net force which acts in a particular direction, and the particle will accelerate in that direction of the net force. So to find the sum of the net forces, we need to take the horizontal and vertical components for each force. Okay, so if we say look at force 1 down here, we can see that it's going to have two components, one in the x direction and one in the y direction. And so will F2 and so will F3. So the way we'd write this out would be like this. So if we look at the force 1 down here, That's going to have a component in the x direction and a component in the y direction. Force 2 is going to have a component in the x direction and a component in the y direction. And force 3 is going to have a component in the x direction and y direction. And we equate that to m times acceleration in the x direction plus m times the acceleration in the y direction. And that is because the acceleration is also going to have components in the x and y directions. So we would write that out like this. So we would write the sum of the forces in the x direction plus the sum of the forces in the y direction equals mass times the acceleration in the x direction plus the acceleration in the y direction. So all I did was factor out m from each term on this side because m is a scalar quantity. So to get the net force in the x direction, I would just add F1 in the x direction plus F2 in the x direction plus F3 in the x direction to get the sum of the forces in the x direction. And to get the sum of the forces in the y direction, I will do the forces in the y direction for force 1 plus forces in the y direction for force 2 plus the forces in the y direction for force 3. So I add this term, and this term to get the sum of the forces in the y direction. So then I can apply Pythagoras to the sum of the forces in the x direction and the sum of the forces in the y direction. Okay, so this is just applying Pythagoras to these two here to get the resultant force, or the net force, which will be this force here. And I'll do the same thing to the acceleration vectors here as well. So I apply Pythagoras to the acceleration in the x direction and the acceleration in the y direction to get the magnitude of acceleration, or the resultant acceleration, which will be this acceleration here. So then I can rewrite this whole expression here as the net force equals mass times acceleration, where the net force is equal to this and the acceleration is equal to this, and m stays as it is. So let's have a look at an example of this. So you can see I've got a 4 kilogram mass here, and I've got 3 forces acting on that. So I've got force 1, which is 2 newtons, force 2, which is 8 newtons, and force 3, which is 5 newtons. And force 3 has an angle of 60 degrees to the horizontal. So let's apply that equation we had. So for force 1, it's got 0 newtons in the x direction. Okay, so force 1 has got 0 newtons in the x direction because it's acting entirely in the y direction. So force 1 has 0 newtons in the x direction, and it's got 2 newtons in the y direction, as shown here. Force 2 has 8 newtons in the x direction and 0 newtons in the y direction. And force 3, we just find its components. So force 3 in the x direction is going to be minus 5 cos 60 degrees, because that component in the x direction would be acting to the left. And force 3 has a component in the y direction of minus 5 times sine 60. That is also going to be negative because that component is acting downwards in the negative y direction. So then we take our sum of the forces in the x direction and the sum of the forces in the y direction, shown by this. So for the sum of the forces in the x direction would give us 5.5 newtons, and the sum of the forces in the y direction will be 2 plus 0 plus minus 5 times sine 60, which would give us minus 2.33 newtons. And we substitute the mass there with 4 kilograms because we were given that, and we don't know anything for the acceleration just yet. So then we apply this method here that we found, so we're just applying Pythagoras of the sum of the forces in the x direction and the sum of the forces in the y direction, and also for the acceleration in the x direction and the acceleration in the y direction, and that will give us this. Okay, so I just substituted in the values to get this, and then simplify that down to get 5.97 newtons equals 4 kilograms times A, and 5.97 is our net force, and that is going to be acting somewhere in this direction here. So our net force is 5.97 newtons. Divide both sides by 4 kilograms to get acceleration, and we get 1.5 meters per second squared. So now we know the particle is going to accelerate with 1.5 meters per second squared in the direction of the net force. And let's say if we want to find what direction that net force has, we just do inverse tan of minus 2.33 newtons divided by 5.5 newtons, and we get minus 22.96 degrees, and that would be this angle here. Okay, so all we're doing is just applying trigonometry. So the force in the y direction was minus 2.33 newtons that we got here, and the force in the x direction was 5.5 newtons, which we got there. So we divide them, do inverse tan, and we get minus 22.96 degrees, and that will be the direction, and that will also be the direction of the particle's acceleration, which has a magnitude of 1.5 meters per second squared. So another important thing to know is that mass always remains constant regardless of the force applied. So if we take our particle there with its mass and we're applying a force in the x direction, it's going to accelerate in the direction of that force with acceleration a. So if we want to calculate mass, we just do force divided by acceleration to get mass. And then if we were to double that force, so we've got 2 times the force in the x direction, which means the acceleration will double. And then if we apply this method, the 2's will cancel out to leave m. So m is always going to remain constant. Okay, and if we quadruple the force and do the same thing, again we get m. So the mass always remains constant. Okay, so let's have a look at weight. Okay, so weight is the mass of the particle multiplied by the acceleration due to gravity. It always acts downwards in the negative z or negative k direction if we're using unit vectors. It always acts from the particle's center of mass, and it's measured in newtons. So weight is commonly mixed up with mass, where some people say weight is in kilograms or pounds, but weight is usually measured in units of force. So the weight is going to be minus m times g, and we have that minus because it's acting in the negative y direction. Okay, g is 9.81 meters per second squared on the surface of the Earth. Okay, so the weight is minus the mass times the acceleration due to gravity, and it's always acting downwards. Okay, so let's say if we had that mass acting on this support down here, so it's just sat on top of that, not moving. Even though the particle is not moving, forces are still present. The weight acts downwards, and there's a normal reaction force that's balancing the weight force. So the weight is always acting downwards, and there's going to be a normal reaction force, which we're going to call N, acting in the opposite direction. So if a force is acting on that particle in the downwards direction, which will be the weight, we can see that the particle won't accelerate, which means it must be balanced with another force. Okay, so that support here must be exerting another force in the opposite direction to keep it balanced, and that is the reaction force. Okay, so weight is always acting downwards, and that's equal to minus m times g, and that is the normal reaction force from the support, which balances the weight, okay, which keeps the particle stationary. Okay, so we write that out like this. So if we find the net force, we're going to get 0 on this side because the acceleration was 0, okay? And then if I add this onto both sides, I can say the normal reaction force equals mg. How does Newton's first and second law relate to this? So Newton's first law says that an object will always stay at rest or in constant motion with a constant speed unless a net external force is acting on it. So in this case, it's at rest, and the net force is going to be 0, so it's going to stay as it is. So that is Newton's first law. Newton's third law says that for every action, there's an opposite and equal reaction. So we've got the weight acting downwards, and the reaction force, which is opposite and equal to that, will be the reaction force. And Newton's second law is just F equals ma, which we have applied here. So friction. The force of static friction, F sub small f, okay, so that is the force of friction, is the minimum force needed to get the particle in motion. The force of static friction acts between the surface the particle is on and the particle. So there is the surface that the particle is on, and there's the particle itself. The coefficient of static friction is dimensionless, and its value depends on the type of surface, for example ice or rubber. So if this particle was on a different surface, let's say if it was on ice, the force you would need to apply to that to get that moving would be much less compared to if it was on rubber. The force of friction does not depend on the surface area of contact between the surface and the particle. So the surface area of contact plays no role. So let's draw in our forces. So we've got the weight acting in the negative y direction, and we've got our reaction force there. So if we apply a force in this direction, and there's friction between the particle and the surface, the force of friction will always act in the opposite direction to the applied force. And that force of friction equals the coefficient of static friction multiplied by the normal force. So that is the force of friction. And the coefficient of static friction here is constant, and that only varies depending on what material the surface is made from. So because we know N, we can substitute N with mg to get this expression here for the force of friction. Okay, and that is the force of static friction. So if the difference between the applied force and the force of friction is less than 0, the particle does not move. Okay, so if we took the difference between this force and it come out to be negative, the particle is not moving. Okay, because this force would be greater than this force. If the difference between the applied force and the force of friction is greater than 0, the particle moves. Because in this situation, the applied force would be larger than the force of friction. If they're equal, if the difference between the applied force and the force of friction is 0, meaning they're equal, the particle is on the brink of movement. Okay, so it's literally just about to move. So a tiny little nudge would get it moving. So the force of kinetic friction is the force of friction present when the particle is moving. So let's say if we applied a force onto that particle to get it moving, even though we've now got it moving, we would no longer say that there's a force of static friction because the particle is no longer static, but it would still have a force of friction. And that force of friction we call the kinetic friction. So the force of kinetic friction. And that is the force of friction present when the particle is moving. So because the object is already moving, we've already overcome that force necessary to get it moving. The coefficient of kinetic friction is going to be less than the coefficient of static friction. Okay, and we would write that like this. So all we did was just take this equation here and just replaced the coefficient of static friction with the coefficient of kinetic friction. And this only applies when the particle is in motion. So if we was to graph the applied force against the force of friction, we would get this graph here. So in this region here, in the static region, the particle is not moving. Okay, so let's say we start off with our applied force as 0. That means the force of friction is going to be 0 because there's no force being applied to that. And as we start to increase that force, the force of static friction will start to increase and increase until it gets to this point here where the difference between the two is 0. So the difference between the applied force and the force of friction is 0. We would define the force of static friction using this equation. Okay, so at this point we can write the force of static friction using this equation, and that's at this point here where the applied force is equal to the force of static friction. In this region down here, the particle's not moving. Okay, so the difference between the applied force and the force of friction does not move. Okay, so that is for this region here. And then if we continue applying that force, eventually the difference between the applied force and the force of friction is greater than 0. And then once that happens, we now describe the force of friction using this equation. So this is the kinetic region. So that means we've applied enough force to get it moving. Okay, so at this point it starts moving and then it goes down a bit. And we define the force of kinetic friction using this equation. Okay, so in this region here, the particle's not moving. And then as soon as it crosses this boundary here, it starts moving. And we say that there is a force of kinetic friction for this region here. And as we said, the coefficient of kinetic friction is less than the coefficient of static friction. So that's why we have this dip here, which goes down. So tension. So let's say if we have this particle with mass m attached to this rope, which is hanging from this support here. Okay, so it's hanging from this wall. So this is going to be static, okay, because it's not moving. So if we draw in our forces, we have weight acting down, so mg acting downwards. And because it's static, there must be another force equal and opposite to mg, which is being supplied by this rope. So that is going to be the tension. So the net force acting on that particle is going to be 0. So we've got mg acting down, and we've got the tension on that rope acting in the opposite direction. So if we look at this rope, okay, the tension on that rope is going to be the same everywhere. Okay, so there's going to be another tension force here as well. Okay, so this tension force is equal and opposite to this here, but it's on the same rope. So the tension has the same value everywhere on the string or rope. It doesn't vary. Okay, so once you've drawn in a tension force on a rope, that tension force is going to be equal everywhere on that rope. So because I've drawn this in this direction, this tension force is going to be acting in that direction. So that must mean that the wall would also be exerting a force on this whole system down here in the opposite direction to keep all of it stationary. Okay, so that force from the wall is equal to that tension in the rope, assuming that the mass of the rope is negligible. So we would say the tension equals mg, and let's say if we took this scenario here where we've got two particles attached with a rope and we're applying a force F1 to the right. Okay, so we're pulling this particle to the right with a force of F1 in the x direction, and we're saying that force is causing this whole system here to accelerate to the right. So we would have a tension force in the rope. So let's say if we wanted to find the force F1. Okay, so the first thing we do is isolate these two masses and have a look at what forces are acting on them. Okay, so for this mass here, mass 2, we'd have F1 minus T, because we've got F1 acting in this direction and we've got tension acting in the opposite direction. So we get F1 minus T equals ma, where the mass was m2 and the acceleration is a. And if we look at mass 1 and look at what forces are acting on that, we just have the tension here. So we just say T equals mass times acceleration, where the mass is mass 1. And because we know T here, we can just substitute that into this equation to get this equation. Okay, so all I did was just substitute T into there. And then I can add this term onto this side to get this, and then factor out A from each term. So this would be the magnitude of the force acting on this system. And mass 1 and mass 2 are going to have the same acceleration because they're connected by this rope, okay? And again, we're assuming that rope has a negligible mass and it can't extend. So let's have a look at the spring force. Okay, so here we have our particle attached to a spring, and at this point here we call the equilibrium position where x, the extension of compression, is 0. Okay, so that is the equilibrium position where the spring is neither being stretched nor it's being compressed. So that is the equilibrium point. So we say that the force, if we was to apply a force to this to either stretch it or compress it, that is always going to equal to the force of the spring. And that force from the spring is always going to act in opposition to whatever force we apply. Okay, so the force of the spring is going to be minus k times x, where k is the spring constant, and that is in newtons per meter. Okay, and x would be in units of length, so meters. So the units would get from k times x would be newtons, and that minus there is just there to tell us that it's always acting in opposition to the force of application. So let's say if we extended that spring using our force F. Okay, so the force F is the force being applied to extend the spring by a length of x from the equilibrium position. The force from the spring is always going to act in opposition, so that's going to be minus kx. So minus kx is the force from the spring which acts in the opposite direction to this force of application to extend the spring by length x. And we would write F equals minus kx. Okay, so the force from the spring is minus kx, and this is the force of application, and they are both equal, but they are going to be opposite. So let's bring that back to its equilibrium position here, x equals 0. This time we're going to apply a force in the opposite direction, so minus F to compress that spring. Okay, this time we're going to apply a force of minus F to compress that spring by a length of minus x, and the spring is going to push back with a force of positive kx, because the force is negative in this direction. That means the spring is going to be positive in the opposite direction. The force from the spring is always going to equal that force of compression there. So if you note here that if x are the same, so if these two x's have the same length, the force from the spring is going to be the same in both situations, and the force of application will also be the same. Okay, so that means from this we can say minus F equals minus k times minus x. Okay, so we've just applied this equation, but we've substituted x with negative x, so that is going to give us minus F equals kx. And again, this is telling us that the force from the spring and the force of application are opposite. So if we was to graph the force of application against the extension, okay, so if we got a force here, okay, and then we double it here, triple it here, and quadruple it there. As we apply these forces, we're going to extend the spring. So if we apply a force of F, we'll extend it by length x, or compress it. It still works out the same either way. Okay, so if we apply this force F, we extend that by length x, and then if we apply a force of 2F, we'll extend that by a length of 2x. and so on. So if we apply that, keep extending it, and we plot the graph, we'll get a straight line like this. And the gradient of this line on the graph will give us the spring constant, K. So the gradient will give us the spring constant. If we had a high gradient here, okay, we'd have a higher spring constant. So that would mean that this here would be for a spring with high stiffness. Okay, so it's going to be stiffer than this spring here because it's got a higher gradient. And if it had a lower gradient, it would be low stiffness. Okay, so this would be for a spring with low stiffness, because you can see here, but for this spring, we had to apply a force of 4F to extend it by length X. So we've had to apply a force 4 times greater to extend it to the length X compared to this one. And for this spring here, we've only had to apply a force of F to extend it by a length 4X. Okay, so for this spring, it would have a spring constant 4 times greater than this, and for this spring, it would have a spring constant 4 times lower than this. So hopefully you can see the pattern there. So spring combinations. So let's say if we had 2 springs connected in series like this, we want to find the total spring constant. So to do that, we just do 1 over kT, where k sub t just means the total spring constant. Okay, so 1 over kT equals 1 over k1 plus 1 over k2. Okay, so that is for springs in series. And then we just inverse that to find the total spring constant. So that is for springs connected in series. For springs in parallel, we can imagine these 2 springs had the same spring constant. It would just double the spring constant. So for that, the total spring constant would just be K1 plus K2. Okay, so that's springs in parallel. And if we had a combination of the two, so these 2 springs here are in series, these 2 springs are in series, and we have a parallel combination of the 2. Okay, so to find the total spring constant, you would find the total spring constant for these 2 springs in series, and for these 2 springs in series, and then add them together. So the total spring constant in series, say for these 2, is going to be 1 over K1 plus 1 over K2. Okay, so that's for the springs in series. And because we have 2 springs in series in parallel, we just add these 2 together. So we just basically times that by 2, okay, to get this. So the gravitational force. So F sub g is the mutual force of attraction between the 2 particles. Okay, so we have 2 particles here, one with mass m1, one with mass m2, where you can see m2 is much greater than m1. And the force of attraction between these 2 is shown by these 2 force vectors here. And r is the distance between the centers of the 2 particles. Okay, so that's r here. So the force of attraction between the 2 particles is going to be mass 1 times mass 2 times g, so big G here, which is the constant of gravitation. Okay, it's a universal constant, which is 6.673 times 10 to the minus 11 meters cubed per kilogram second squared. Okay, so that is the value of g, and we divide that by r squared, so the force would vary according to the square of the distance. Okay, so let's say if the force of attraction between these 2 particles is 1 Newton. Okay, just keep it simple, so let's just say it's 1 Newton, and the distance between them is 1 meter. So if we was to double the distance between these 2, the force between the 2 would be 1/4. And then if we was to double it again, between the 2 would be 1/16, okay, and so on. So that is the inverse square law, and that's what this r squared on the bottom here describes. Okay, so the force between the 2 varies according to the inverse square of the distance between them. We can also say that the force of attraction between the 2 is m1 times g2, where g2 is the acceleration due to the gravitational field of mass 2, and we can say g2 equals m2 times the universal gravitational constant g divided by r squared. Okay, so that's just mass times acceleration, and the acceleration for this situation is going to be the acceleration due to the gravitational field of mass 2. And likewise, we can say that the mutual force of attraction equals mass 2 times g1, where g1 is the acceleration due to the gravitational field of mass 1. Okay, and that is equal to mass 1 times universal gravitational constant divided by r squared. So if we wanted to calculate what the acceleration due to gravity is of mass 2, okay, we would use this equation here. And if we wanted to calculate what the acceleration due to gravity for mass 1 is, we would use this equation here. And the acceleration due to gravity varies with the distance it is from the other particle. So for example, let's say if we had Earth here, and let's say if we want to calculate its acceleration due to gravity, we would use this equation here. Okay, so that would be the mass of the Earth times the universal gravitational constant divided by the radius of the Earth squared. Okay, so that is the radius of the Earth here from the center of the Earth to the outer edge of it. Okay, so that will be r down here. And if we look up the values for the mass of the Earth and the radius of the Earth, and we use g from here and substitute those in, we'll get 9.81 meters per second squared. So that is basically saying if we had a mass on the surface of the Earth here, its acceleration due to gravity would be 9.81 meters per second squared. And we can also say that mass 1 would have an acceleration g2. Okay, so that would accelerate with an acceleration of g2. Okay, and mass 2 would accelerate with an acceleration of g1. And because mass 2 is much greater than mass 1 is going to have a larger acceleration than mass 2. Okay, but they are both accelerating, just one more so than the other. Okay, so here's our summary. So these are all the forces that we found. So we found the net force equals mass times acceleration, and we know the weight equals mass times the acceleration due to gravity, and the force of friction equals the coefficient of static friction times the normal force, and we know the force from a spring is minus kx. Okay, and we found the force, and we found the mutual force of attraction between two masses with this equation here. So we can also write this as just F equals ma, or we could write that as F equals m times d2x by dt squared. Okay, so that is acceleration. And we can also write that as F equals m times x double dot. Okay, and for this here, we can also say that the normal force is mg. So we can say that the force of static friction equals the coefficient of static friction times mass times g. And we also found that the force of kinetic friction equals the coefficient of kinetic friction times mass times g. So this is the force of friction when the particle is in motion. And because we know F equals m times x double dot, and we know F equals minus kx, we can therefore say m times x double dot equals minus k times x. Okay. From this, we can say that the force of attraction equals mass 1 times the acceleration due to gravity of mass 2, and we can also say that the force of attraction equals mass 2 times the acceleration due to gravity of mass 1. Okay, so write these down because we will be applying these equations later on. Okay, so now we've introduced Newton's second law and the types of forces. We're now going to look at some applications with Newton's second law. So here's our mass inside this XYZ coordinate system. Okay, so I'm going to introduce these unit vectors I, j and k. So hopefully by now you are familiar with these. All these are just unit vectors, so their length is just 1, and I points in the direction of x, j points in the direction of y, and k points in the direction of z. So if we're applying a force in the x direction, the y direction, and the z direction, we can write all of that out in vector form like this. So we find the sum of the forces of the force x, which is going to be in the I direction, so we multiply that by the unit vector I. So even though we've multiplied that by the unit vector I, it hasn't changed anything. It's only telling us that it's in the I direction, and the force F sub x is going to cause this particle here to accelerate, which again is in the direction of I, and the force y here, so we find the sum of the forces in the y direction times the unit vector j, and that is going to cause this particle to also accelerate in the j direction, shown here. And we're applying another force, F sub z, which is going to cause this particle to accelerate in the direction of k. So if we want to find the total sum of all the forces, we just add all of these forces together. Okay, so this is written in vector form. So this is the sum of all the forces. And then if we want to find the magnitude of those forces, we apply Pythagoras to that. Okay, so the sum of the forces in the I direction squared, sum of the forces in the j direction squared, sum of the forces in the k direction squared, and then square root that, we get the magnitude of the sum of the forces. Okay, we do the same thing for acceleration. Again, apply Pythagoras to get the magnitude of acceleration. So now we know the magnitude of the force and we know the magnitude of the acceleration. We can just write all that down as sum of the forces equals mass times acceleration. So we've just boiled this down to F equals ma. Okay, both cases are F equals ma, but this is just written out as the net force equals mass times the net acceleration. But in our applications, we will start off by using this over here, and then eventually working our way down to just get F equals ma to solve our problems. Okay, so it's probably worth writing this down as well. This forms the basis of what we're going to be doing next. Okay, so what I have here are two masses, m1 and m2, okay, and the force F is being applied onto mass 1 in this direction, and that is going to cause these two masses to accelerate together, and both masses are on a frictionless surface. Generally, when we're doing problems like this, okay, we always draw in our xy coordinate axis here, and we are trying to find the acceleration of these two masses. So the first thing we want to do is draw a free body diagram identifying all the forces. So what we basically do is isolate each mass, have a look at each one, and identify all the forces acting on each mass, and then we use that in our calculations. So we want to know what forces acting on each mass in the x and y direction for each one, and I've also drawn in their center of mass. Okay, so there's our first force. So we've got mg acting down for mass 1 and mg acting down for mass 2. And we're going to have these two normal reaction forces, so N1 for mass 1 and N2 for mass 2. And these two are going to be equal because there is no acceleration in the y direction. And we also have a force acting on mass 2 from mass 1. So we say the force that mass 1 exerts onto mass 2 is going to be in this direction. And we have a force that mass 2 exerts on mass 1 in the opposite direction. So as this force is applied on these two particles, this mass is going to exert a force onto this mass, and this mass will exert a force onto this mass. And we're going to say the force that mass 1 exerts onto mass 2 is going to be F, and the force that mass 2 exerts onto mass 1 is going to be minus F. So we're going to isolate the masses and apply our method. So for mass 1, the sum of the forces in the x direction is going to be F, which is in the positive direction, minus F, okay, because this force is being applied onto mass 1, okay, and we said the force that mass 2 exerts onto mass 1 is negative, so we get this negative here. And the sum of the forces in the y direction is just going to be N1 equals M1 times G, okay, because these two forces are equal. And for mass 2, the sum of the forces in the x direction, so if we look at mass 2 here, what forces are acting on this mass in the x direction? It's just going to be the force that mass 1 exerts onto mass 2. And remember, the force that mass 1 exerts onto mass 2 is positive F over here. So we're just going to say F equals ma, like that, where m was just for mass 2. And the sum of the forces in the y direction is going to be N2 equals mass 2 times g. And then if I substitute F into here, so what I'll do is replace F with m2 times ax, I'll get this equation. Okay, so if I add this term to both sides and factor out a, I'll get this. And then if I divide both sides by m1 plus m2, I get the acceleration of the system. Okay, so the acceleration of the two masses. Okay, so that's one example of how we apply Newton's second law using free body diagrams. Okay, so what you want to do each time you see a problem like this with multiple masses, you isolate each mass and you look at what forces are acting on each mass in the x and y direction, and then you find the net force for each mass and then equate that to mass times acceleration, and then from that point you can then make your substitutions to find what you're looking for, just like we did here. So here's another application. So we've got these two masses here, so small m for this mass and big M for this mass, and they're connected by this cable, and shown by these arrows the motion is happening in this direction. Okay, so this mass is moving downwards and this mass is moving to the right. Okay, and they're both connected by that cable, and because they're both connected by that cable, that means they're both going to have the same acceleration, because however much this moves, this is going to move by the same amount. Again, we isolate our masses and find what forces are acting on each mass. So for this mass here, we're going to get mg, and there's our normal reaction force for this mass, so N, capital N, and there's our force of friction, which acts in the opposite direction to the motion of mass m. Okay, so that's acting between the mass m, small m, and the surface, so that always acts in the opposite direction. And for this mass, we're going to have mg acting downwards, shown by the negative, and we're going to have the tension in this cable here and here. Okay, so the tension T is the same here and the same there. They just act in opposite directions. So you can imagine this mass is trying to move down and this cable is trying to pull it back up. And as it moves along, the tension in this cable is pulling this mass to the right. So again, we isolate our masses and apply our method. So for mass small m, the sum of the forces in the x direction is going to be T minus the force of friction, because we've got T acting in the positive x direction and the force of friction is in opposition to that in the negative direction, which is how we get negative there. So this is our net force in the x direction, and we equate that to mass times acceleration in the x direction. So then we can substitute the force of friction by the coefficient of kinetic friction times mass times g, and it's the coefficient of kinetic friction because the system is moving, okay, so it's accelerating. And the sum of the forces in the y direction for this mass is just going to be n equals mg, because these two forces are equal, as there is no acceleration in the y direction, meaning there is no net force. And for mass big M down here, the sum of the forces in the x direction is going to be 0, because if we look at this mass, there's no forces acting on it in the x direction. So the sum of the forces in the x direction is going to be 0, and the sum of the forces in the y direction is just going to be minus big M times g, because that's going in the minus y direction, plus t, because that's in the positive y direction, equals big M times a sub y, which is the acceleration in the y direction, and that's negative because it's going to accelerate in the negative y direction. So that means we can say that the acceleration in the y direction equals the acceleration in the x direction, because they're connected by this cable. Okay, so the acceleration for each mass is the same. So that means I can replace a sub y here with a sub x. Okay, and then if I just add this term to both sides, replace a sub y with a sub x, I get this. And then I can rewrite that like this by just swapping these two terms over. It's the same as this. And then I can substitute t into here, because I know the two tensions in that cable are going to be the same, because remember, earlier on we said the tension in the cable is the same everywhere. So that means I can substitute t into here to get this. And then all I did was just add this term to both sides to get this, and then factor out a g from here, factor out a from here to get this, and then I could just divide both sides by small m plus big M to get the acceleration of the system. And that is another example of how we apply Newton's second law, where there's two masses connected by a cable. So now we're going to look at the inclined plane problem. So what we have here is our mass, okay, our particle with mass small m, and it's on an inclined plane, and that is inclined through an angle of theta. And again, notice that we have changed our xy coordinate axis here so that x is parallel with this inclined plane. So we're saying motion up and down the incline is in the x direction, and motion perpendicular to that is in the y direction. So we draw our free body diagram identifying all the forces. So we have mg acting down. So although it's inclined, mg always acts downwards. A common mistake would be to think that mg acts in this direction here, perpendicular to the inclined plane. That is incorrect. So the weight of that particle is always acting downwards. So that means we have a component of that weight in the y direction. So we can draw that component of weight in, which is minus mg cos theta, okay, because the angle between mg and mg cos theta is going to be the same as the angle of the incline. So if you was to imagine if we took this incline and then brought it down so that theta was 0, this vector here is going to start moving closer and closer to this, which would make it 0. Okay, so therefore we can say this angle and this angle are the same, and we have the normal reaction force acting in this direction. So that normal reaction force is equal to this component of the particle's weight. And we also have a component of weight acting in the minus x direction. So we can also imagine that's here. So if we want to complete the triangle here, this would be minus mg sine theta, which acts down the incline. So that's in the negative x direction. Okay, so what we have is the weight of the particle acting downwards, and we have its component of weight acting in the x and y direction. So the component of the particle's weight in the y direction is going to be minus mg cos theta, and the component of weight acting in the x direction is going to be minus mg times sine theta. And we have our force of friction here between the particle and the inclined plane, acting in the opposite direction of its motion. So we're saying it's static. What's actually keeping it static is the force of friction, because this particle wants to go in this direction, but the force of friction here is preventing it from doing that. However, if we incline this plane more, eventually this particle would start sliding down, because this component of the particle's weight would exceed the force of friction, which would cause it to accelerate down the incline. However, we are saying this is static. So we use our equation that we found earlier on. So the sum of the forces equals the sum of the forces in the x direction plus the sum of the forces in the y direction plus the sum of the forces in the z direction. And because we're only looking at this in 2D in the x and y direction, this term is going to go to leave behind this. Okay, so we want to find the sum of the forces in the x direction and the sum of the forces in the y direction. So if we find the sum of the forces in the x direction first, we're going to have minus mg times sine theta, because that's acting in the negative x direction, plus the force of friction equals 0. And we're saying it's equal to 0 because we're saying this particle is static, so it's not accelerating. And then I can replace the force of friction there with the coefficient of static friction times the normal force. Okay, so we saw this earlier on. And then I can add this term to both sides to get this equation here. And then if I find the sum of the forces in the y direction, okay, so if I look at the mass, what are the forces in the y direction? So I'm going to have n and minus mg cos theta. And that is again going to equal 0 because there's no acceleration in the y direction. So I can add this term to both sides to get this. And then if I take n here and substitute that into there, I'll get this equation. And if I divide both sides by mg cos theta, I'll get this equation here. So the mg's will cancel out, and sine theta over cos theta we can write as tan theta. What we have here is the coefficient of static friction equals tan theta, okay? And theta would be the angle that we would move this incline to the point where this mass is literally just about to start sliding. Okay, so this angle would be whatever angle we put this, so that the force of friction and this component of weight are going to balance out. And from this we can also say that the coefficient of static friction times mg cos theta equals the force of friction. Okay, so the force of friction is going to vary with theta. However, this condition only applies when the coefficient of static friction is greater than or equal to tan theta. Tan theta, so tan of whatever angle we put this incline at, has to be less than or equal to the coefficient of static friction. Okay, so if theta exceeds a certain limit, this mass will start to slide. And we can also say that theta has to be less than or equal to inverse tan of the coefficient of static friction. So if we did inverse tan of the coefficient of static friction, that will give us an angle theta where the force of friction and this component of weight are going to be equal. However, theta has to be less than or equal to that angle for this condition to apply. Okay, so if theta exceeds inverse tan of the coefficient of static friction, this particle will start to slide. Okay, so now we're going to say that the particle is sliding. Okay, so if we look at some of the forces in the x direction, we have this. So we have minus mg sine theta plus the force of friction, because that's in the positive x direction, and we say that's minus m times ax, because this mass now is going to start accelerating. Okay, and it's minus because it's going to accelerate in the negative x direction. And then if I add this term to both sides and substitute the force of friction with the coefficient of kinetic friction times the normal force, I get this. Okay, and it's the coefficient of kinetic friction because now the particle is sliding downwards. Okay, so we're saying that theta has exceeded that limit. Okay, so theta has exceeded inverse tan of the coefficient of static friction, so now it's sliding downwards. And then we can factor out m from each term over here, and then I can swap these two terms over like this. And then if I divide both sides by n, I get this expression here. And now if I look at the sum of the forces in the y direction, I get this, because again there's no acceleration in the y direction. So I've got n, which is in the positive y direction, minus mg cos theta, which is in the negative y direction, and that is going to equal 0. So I can add this term to both sides to get n equals mg cos theta. And then if I substitute the normal force here into here, I'll get this equation. Okay, so that is for the coefficient of kinetic friction. And then these two masses are going to cancel out to leave behind this. And then if I expand this, okay, so I'll do 1 over g times cos theta times g times sine theta. The g's will cancel out and we can write sine theta over cos theta as tan theta. And then if I multiply this by ax, I get this term here. Okay, so if you remember, we said that the coefficient of static friction equals tan theta. Okay, so we can see here that the coefficient of kinetic friction is going to be less than the coefficient of static friction, like we said earlier on. So we can say that here. And that is how much less it is than the coefficient of static friction. So for this condition to exist, so for this to apply, theta would have to be greater than inverse tan of the coefficient of static friction. So this condition must exist for this to apply. So let's have a look at this example here. So we've got these two masses, small m and big M. Again, these two are connected by a cable, and this mass is on an inclined plane. Okay, so notice we have two coordinate axes here. So this coordinate axis has been made parallel with the incline, and this coordinate axis here is how we saw it before. So let's do our free body diagram. So that is the weight of m, which is minus mg, and we have that component of weight there, and we have the normal reaction force here, and we have this component of weight in the x direction. And we can also draw that here as well to make it easier for you to visualize. And we have friction acting in the opposite direction of motion because this particle is going in this direction. That means the force of friction and its component of weight is going to oppose its motion. And for this mass we have minus big mg acting down, and we have the tension there in the rope like we saw earlier on, and we also have it there as well. Okay, so isolate the masses and apply the method. Okay, so for mass small m, the sum of the forces in the x direction is going to be T minus mg sine theta minus the force of friction. Okay, so T minus mg sine theta minus the force of friction. Okay, and the sum of the forces in the y direction for this mass is just going to be N equals mg cos theta. And for mass big M, the sum of the forces in the x direction is going to be 0. Okay, because there's no forces acting on that mass in the x direction. And the sum of the forces in the y direction is going to be minus big mg acting downwards plus T, because that's acting in the positive y direction, equals minus big M times a sub x. Again, we're saying a sub y, so the acceleration of this mass in the y direction equals the acceleration of this mass because they're connected by this cable, and that is minus because it's going in the minus y direction. And then we add this term to both sides, and then we can swap those two terms over like this. And then if I substitute t into here, I'll get this equation here. So I just substituted t into there to get this. And then all I did here was just add this term to both sides, because everything with an a sub x I want to get onto one side to get this over here. So all I did here was replace the force of friction there with the coefficient of kinetic friction times mg times cos theta. So we've seen that before. And because earlier on we found the coefficient of kinetic friction equals tan theta minus a sub x over g cos theta, we might be tempted to substitute this into there. If we did that, we'd end up with g equals a sub x. But this can't be the case because the particles cannot be accelerating with an acceleration of g. So this doesn't work in this situation, so that does not apply. Earlier on when we found it, the force of friction was acting in the opposite direction and there was no tension, okay, when we looked at it for the inclined plane. So the situation is different, so we're going to get different equations this time. Okay, so you have to be careful how you apply Newton's second law and where you draw these forces in. If you try to apply it from one situation to another, it just won't work. So if I just add this term to both sides, I'll get that, and then if I factor out a sub x from each term to get this, and then subtract both sides by this term to get this equation here, and then divide both sides by mg cos theta, I get the coefficient of kinetic friction as this. Okay, so you can see this is different to this. Okay, and the reason is because, again, we have different forces acting on the objects, and it's a completely different situation, so you have to be careful how you apply these. Okay, so we're going to look at a mass and spring with friction. Okay, so this is the equilibrium position here, and we've just applied a force F to extend this mass by displacement x. Okay, and the force of friction is going to be acting in the opposite direction to motion, and we also have the force from the spring acting in the opposite direction to the force of application. So all I did was apply this force onto this mass to extend it by length x, and we have our force here that we're applying, and we also have friction and the force from the spring acting in the opposite direction to the force F. And again, we have mg acting down, and we have our normal force there. So if the spring was being stretched continuously, so if we kept stretching that, that means there's going to be an acceleration. Okay, so that means the mass there is going to accelerate. If we take the forces in the x direction for this situation, we get F minus the force of friction minus the force from the spring equals m times a sub x. And it's m times a sub x because the particle is accelerating because of the continuous force being applied to that. Okay, and the forces in the y direction is just going to be n equals mg. And then I can rewrite the force of friction there as the coefficient of kinetic friction times mg. And I get this equation here. If the spring is being stretched but isn't moving, okay, so I've just stretched the spring with a force F and then just kept it at that point, that means the acceleration in the x direction is going to be 0. So all I did was just stretch that with a force F and just kept it at a point x. I'm going to get this equation, so F minus k times x. This time there's going to be no friction because it's not moving. And then I can say F equals kx. And the sum of the force in the y direction is just going to be n equals mg again. Okay, so now that we've applied Newton's second law, we are now going to complete 6 example problems for you to have a look at. So example 1. The block is pulled up an incline of theta equals 35 degrees with a force F equals 100 newtons in the direction shown. If the coefficient of kinetic friction mu sub k between the block and the incline is 0.4, find the normal force and the acceleration of the block. Okay, so what we have here is a block with a mass of 5 kilograms, which we're treating as a particle, and it's being pulled up the incline with a force F equals 100 newtons. Okay, and it's at an angle of 15 degrees to this line here, which is parallel to the incline. And again, notice that our XY coordinate axis has been rotated so that X is parallel to this incline, and the incline has an angle of theta equals 35 degrees. Okay, so let's draw our free body diagram identifying all the forces. So there's F sub x, which is a component of the force x in the positive x direction, and there's F sub y, which is a component of x in the vertical F sub y direction. Okay, so in the y direction. There's our weight acting downwards, so it's minus mg, okay, and that's from the center of mass of this block. And there's our component of weight in the y direction, which is minus mg times cos theta. Okay, and again, notice that this angle and this angle are equal. And there's our normal force on the incline. And there's our component of weight, which is minus mg sine theta, which is in the minus x direction. And again, notice that the question has told us that there's a coefficient of kinetic friction of 0.4 between the block and the incline. So that means there's going to be a force of friction in the opposite direction to its motion. And its motion is going up the incline, because the question has told us that F is pulling this block up the incline. So the force of friction is going to be in this direction here, and that is the force of kinetic friction. So the sum of the forces in the x direction is going to be F sub x, which is in the positive x direction, minus mg sine theta minus the force of friction equals m times a sub x, which is the acceleration in the x direction, and that is positive because we know the block is being pulled up the ramp in this direction. So then I substitute the force of kinetic friction with the coefficient of kinetic friction times the normal force. So from this point, I'm going to assume that you know about this. You know that the force of friction equals the coefficient of kinetic friction times the normal force. Substitute all my numbers in, and don't get confused between n here, which means newtons, so for example 100 newtons, and n, the normal force here. So one is in italics and one isn't in italics, and it's usually bold. Okay, so for example this n and this n, try not to get confused between the two. I couldn't think of anything else to use, so you're just going to have to not get confused between n and the normal reaction force. So this means newtons and this means the normal force. So simplify that down to get this. Then I find the forces in the y direction, and that is going to be n, which is in the positive y direction, plus F sub y, which is this component of the force in the positive y direction, minus mg cos theta, which is acting in the negative y direction. And that is going to equal 0 because there's no acceleration in the y direction. So we're assuming that this component of force in the y direction for F isn't strong enough to lift it off the incline. Okay, so we're assuming it's being pulled upwards along the incline. Okay, so I add this term to both sides and subtract this term from both sides to get this. Substitute all my numbers in again, and I get the normal force as 14.3 newtons, and that answers the first part of the question. Okay, so we found n, so n here, the normal force, has 14.3 newtons. Okay, And then next what I can do is take this and then substitute that into here, okay, to get 5.72 newtons. Simplify this down to get 62.75 newtons equals 5 kilograms times A sub x. Rearrange that for A sub x, so dividing both sides by 5 kilograms, and I get the acceleration is 12.55 meters per second squared. And that answers the last part of that question. So example 2. Two trailers, each with a mass small m equals 500 kilograms, are pulled by a truck with a mass big M equals 1000 kilograms, which creates a driving frictional force at the wheels which varies in time. So we're given the frictional driving force as a function of time. If the truck starts from rest, how fast is it going after 3 seconds? Also, what is the tension T in the rope between the first trailer and the truck at this instant? So firstly, you'll notice that the acceleration due to gravity is 9.81 meters per second squared. And there's our coordinate axis, the XY coordinate axis. And I'm very quickly going to draw in the free body diagram, which is that. Okay, and the frictional driving force is acting here between the wheel and the ground, and it's in this direction, so the positive X direction. So a common mistake is to think that the frictional driving force acts in the opposite direction. Okay, it doesn't, it acts in this direction. So if you imagine as this wheel spins round, the tires go in this direction, and the friction force in opposition to that would be in this direction here, so it's going to be in the opposite direction. So the driving frictional force at the wheels is in this direction. Okay, so sum of the forces in the y direction is going to be 0, because this force equals the weight, this equals the weight, and this equals the weight here. And the sum of the forces in the x direction is going to be F equals m times a sub x, where m is just the combined mass of the whole system. Okay, so if we substitute the frictional driving force with 20T, because it's given to us here, and we substitute m with 2 times small m, where small m was a mass of each trailer, and we've got 2 of those, so we times that by 2, plus the mass of the truck, which was 1000 kilograms. So if we substitute all that in, we get 20T equals 2000 kilograms times a sub x, which is the acceleration of the whole system in the x direction. So rearrange that for a sub x to get 0.01t equals a sub x. And we also know that dv sub x by dt equals a sub x. So this is just the time derivative of velocity to get acceleration. So times both sides by dt to get this equation here. Integrate both sides. So I'm integrating this side from 0 to v and this side from 0 to 3 seconds. Do the integration, evaluate the limits, and I get v is 0.045 meters per second. So that is the velocity of the whole system there, okay, at 3 seconds. And that answers the first part of the question. So I'm going to keep this to one side, okay, because this is the acceleration, so we will need that at some point again. So the tension is going to be acting in this direction on the rope. Okay, so if I isolate the truck and look at what forces are acting on that, I get the force of friction is going to be in this direction, and the tension in this rope is going to be in this direction here. So we are trying to find the tension of the rope between the first trailer, this trailer here, and the truck at 3 seconds. So the sum of the forces in the x direction for the truck is going to be the frictional driving force minus T, okay, because we know this frictional driving force is going to be greater than the tension force because we know it's moving in this direction, and it's accelerating because there's a net force acting on that truck. So substitute m there with 1000 kilograms because that is a mass of the truck. So to get this, and we substitute a sub x with 0.01t. So we evaluate this at 3 seconds, so we substitute t there and t here with 3 seconds to get this. Simplify that down to get that, and then we solve for t, so the tension, and we get t equals 30 newtons. And that answers the second part to this question. So example 3. A 15 kilogram block is being lifted by an elevator which has a mass of 300 kilograms. The elevator travels up with a constant acceleration a equals 2 meters per second squared. Find a, the normal force of the block, b, the tension T in the cable, c, the normal force and acceleration of the block if the cable was cut. Okay, so isolate the two masses and draw our free body diagram. Okay, so for this block here, we're going to have mg acting down, and I'm going to say small m is the mass of that block, so 15 kilograms, and we have the normal force acting in this direction here. And there's the weight of the elevator there, and there's the tension in the cable here. So if we wanted to know the net force of the block, we would just do the normal force subtracted by mg. So for the block, okay, the sum of the forces in the x direction is going to be 0, and the sum of the forces in the y direction for the block is just going to be n minus m times g equals ma. Okay, so it's equal to ma because a here we're given is 2 meters per second squared. So the elevator and the block is going to be accelerating upwards with an acceleration of 2 meters per second squared because they're attached. Okay, so they're connected together. Okay, so add mg to both sides, factor out m, substitute our numbers in. So m was 15 kilograms, a was 2 meters per second squared, g was 9.81 meters per second squared, given here. And then put that into my calculator and I get the normal force equals 177.15 newtons. Okay, so that is the answer to part A. So for the elevator now, the sum of the forces in the x direction is going to be 0. The sum of the forces in the y direction is going to be T minus G times small m plus m. Okay, so we have to include the mass of the block as well, equals ma, where m is the mass of the block plus the mass of the elevator. Okay, so this is the sum of the forces in the y direction. So we substitute our numbers in. So we knew G, so we knew the mass of the block, we knew the mass of the elevator, and then we add them together to get 315 kilograms. And it was the same thing here, so 315 kilograms, and we knew A was 2 meters per second squared. So add 3090.15 newtons to both sides to get this. Simplify that down to get T equals 3720.15 newtons. And that is the answer to part B. So now we need to find the normal force and acceleration of the block if the cable was cut. Okay, so the sum of the forces in the x direction for the block is 0, and the sum of the forces in the y direction for the block is going to be this. Okay, so, and we equate that to ma, where m is just the mass of the block, and it's minus because once that's cut, it's going to drop down in the negative y direction, and it's going to have an acceleration of g, so we substitute a with g. So I add mg to both sides to get this, factor out m, substitute my numbers in, and I get the normal force is going to be 0 newtons. Okay, so if that cable was cut, the normal force on that block, on that elevator, is going to be 0. And that is the answer to part C. And also note that the tension will also be 0, and the acceleration of the block would be g. So example 4. The block with mass m equals 150 kilograms is attached to the springs in the arrangement shown. So this arrangement here, each spring has a spring constant K equals 100 newtons per meter. Find how much the mass moves down when it's released. Okay, so basically we have this mass attached to this spring system here, and once it's attached and then released from its equilibrium position, we want to know how far it's going to drop from its equilibrium position. Okay, so that's basically what this question is asking for. Okay, so we draw our free body diagram, so we're going to have mg acting down. Okay, so m is just the mass of this block, which is 150 kilograms, and we have the combined spring force from all these springs pulling in the opposite direction. Okay, so that is the combined spring stiffness times the distance it's moved from its equilibrium position, which is x. So the sum of the forces in the x direction is going to be 0. So first we need to find the total spring constant, which is going to be this. Okay, so if we take these 3 springs here and add them up to get 3k, we can imagine that there's one spring here with a spring constant of 3k, and that spring with a spring constant of 3k is connected in series with this spring here, which has a spring constant of k. This here, so 3k, is the combined stiffness for these 3 springs, and because they're in series with this spring, we write it like this. Okay, so 1 over k sub t, which is the combined spring stiffness, equals 1 over 3k plus 1 over k. So rearrange that for k sub t to get this, so 1 over 3k plus 1 over k. Substitute our numbers in, multiply 3 by 100 to get 300 newtons per meter over here. Put that into my calculator to simplify it down to this, and I get a combined spring stiffness of 75 newtons per meter. Okay, and then I find the net force acting on that block, okay, which is going to be the total spring constant times x minus mg equals 0, and it's 0 because when it's released, it's eventually going to stop accelerating at a certain point, and it will be a certain distance x from its equilibrium position. However, its acceleration at that point will be 0, which is how we get 0 here. So add mg to both sides, divide both sides by the combined spring constant, and we get x equals mg over k sub t. Substitute our numbers in, so we knew the mass was 150 kilograms, we knew g, and we know the combined stiffness of the spring is 75 newtons per meter. So substitute that in as well, and we get 19.62 meters, and that is the answer to this question. So when this block is released from its equilibrium position, it would move 19.62 meters from that equilibrium position. So example 5. 2 planetary bodies with mass m1 equals 150,000 kilograms and M2 equals 75,000 kilograms are 200 kilometers apart. The meteorite has mass M equals 5,000 kilograms, is moving between the two bodies. Find the distance x the meteorite should be positioned in order to remain stationary between the two bodies. Also find the acceleration due to gravity g1 and g2 for the two planetary bodies at this instant. Okay, so we have these two planetary bodies here, 200 kilometers apart, so the distance from the center of each of those two planetary bodies, and we have a meteorite in between, okay, and we want to find at what distance x should this be positioned in between these two bodies so that it's stationary. Okay, so that means the mutual force of attraction between M1 and the meteorite is going to equal the mutual force of attraction between M2 and the meteorite. If that condition exists, then the meteorite will stay stationary. Okay, so if we draw in our free body diagram, so this is the mutual force of attraction between M1 and M. This is the mutual force of attraction between M2 and M here. So in order for that to stay stationary, F sub g here, the mutual force of attraction, has to be equal on this side and this side. We can apply this equation now for this mutual force of attraction here and this force of attraction here. So these two need to be equal, okay? So if they're equal, that means I can say the force of attraction between M1 and M is going to be M1 times M times G divided by D minus X squared. So we're saying D equals 200 kilometers. So if we did D minus X, we would get the distance between M1 and M, and that is this distance here. Okay, so we square that. Okay, so that's what we use for the distance between M1 and M, and we have minus M2 times M times G over X squared. Okay, and X is the distance between M2 and M. And remember, this here is the mutual force of attraction between M1 and M, and this is the mutual force of attraction between M2 and M. And we are saying those two are equal. Okay, so I've equated them and then just subtracted this term from both sides. Okay, so then I can add this term to that side to get this. So what I did was add this term to this side and this side. The m's cancel out, so this m and this m would cancel out. And then I multiply both sides by x squared and divide both sides by m1 to get this. And then square root both sides, because I've got a squared there and a squared here. I want to square root both sides to get rid of the squares because I'm trying to get x on its own. And that's going to leave behind this. Okay, so that squared and that squared cancel out with the square root to leave behind this. So put my numbers in for m2 and m1 to get this, and I know x over d minus x is going to equal 0.707. So continuing on, then times both sides by d minus x, expand the brackets to get this, and then add this term to this side. So I just added 0.707x to both sides to get this, and then I can factor out x to get this, and then divide both sides by 1.707 to get this expression here. Substitute d equals 200 kilometers, so that's going to be 200,000 meters, and then that simplifies down to x equals 82,835.38 meters. So that is the answer to the first part. So this is basically saying that this meteorite has to be positioned a distance x from M2, where the length of x has to be 82,835.38 meters. So I want to find the acceleration due to gravity g1 and g2 for the two planetary bodies. So I want to know what the acceleration due to gravity of m1 is at this instant, and I want to know the acceleration due to gravity for m2 at this instant. So for g1, I'll just do m1 times g over r squared. So if I just use r equals 200,000 meters minus 82,835.38 meters. Okay, so I'm using this distance here, so the distance r. So substitute all those values in, put it into my calculator, and I get g1 equals 7.29 times 10 to the minus 16 meters per second squared. And that is the acceleration due to the gravitational field of mass 1. And now I want to find the same thing for mass 2. So the acceleration due to gravity for mass 2 is going to be m2 times g over r squared. And I'm going to replace r there with x, because that is the distance between m2 and m. So again, substitute those numbers in. So I substituted x into r, substituted m2, substituted g, which was our universal gravitational constant. Simplify that down to get g2 equals 7.29 times 10 to the minus 16 meters per second squared. So notice that g2 and g1 are the same. If this mass is stationary, that means the force of attraction between this mass and m2 is going to be the same as the force of attraction between mass 1 and this mass, and the acceleration due to gravity is going to be the same, but notice that this mass is much further away from M1 than it is from M2. In order for the acceleration due to gravity of this mass to be the same from each mass, this would have to be further away from this, and the reason this would have the same acceleration due to gravity as this mass here is because it's got more mass. So example 6, part 1. Yeah, that's right. So this is part 1. So there's 2 parts to this question. So there's example 6 part 1, and there's going to be an example 6 part 2 as well. Okay, so 2 blocks are connected together by a cable which passes over a frictionless and massless pulley. The blocks both move on a frictionless surface. Determine A, which way will the system move when the blocks are released from rest? B, the acceleration A of the blocks. C, the tension T in the cable. First thing I'm going to do is draw my coordinate axis. So I've got a coordinate axis for this side of the incline, okay, where X is parallel to this side of the incline, and Y here is normal to the incline. On this side, X again is parallel to this incline, and Y is normal to this incline on this side. So I'm going to call this mass M1, and I'm going to call this mass M2. So M1 is 10 kilograms, and M2 is 5 kilograms. So I'm going to draw in my free body diagram. Okay, there it is. So hopefully you're familiar with that by now. Okay, so for mass 1, I've got its normal force, I've got its component of weight acting downwards, and they're both in the y direction. And I've got minus m1 times g times sine 40 degrees, which is in the negative x direction, and the tension in the cable is in the positive x direction. Okay, so similarly for mass 2, I have the normal force and its component of weight acting in the y direction, so the negative y direction, and n2 is in the positive y direction. And I've got m2 times g times sine 61.5 degrees going in the positive x direction, and the tension here is going in the negative x direction. Okay, so that is my free body diagram for that. So hopefully you're up to speed on that by now. So we're going to isolate our masses and apply our procedure. So for mass 1, sum of the forces in the x direction is going to be minus m1 times g times sine 40 degrees plus t equals m1 times a. So that is Newton's second law. So this side is the net force in the x direction for mass 1, and I've equated that to ma, where m was just mass 1. The sum of the forces in the y direction is going to be minus m1 times g times cos 40 degrees plus n1. Okay, so remember the minus there is telling us that this force is acting downwards, and plus n1 because the normal force is acting in the positive y direction. And for mass 2, we have the sum of the forces in the x direction as m2 times g times sine 61.5 degrees minus t. Okay, so this force here is positive, this force is negative because t is going in the negative x direction, equals m2 times a. And again, just in case you didn't notice, this a and this a are going to be the same. These 2 blocks are connected by this rope, so they will have the same acceleration. Okay, then I take my forces in the y direction to get this. Okay, so minus m2 times g times cos 61.5 degrees is this force here, plus n2, which is in the positive y direction, equals 0. So there's no acceleration in the y direction, and there's no acceleration in the y direction for this block either. So the question is asking us to find acceleration and tension. Okay, so you can see here this equation doesn't contain tension or acceleration. This equation contains no tension or acceleration. So these 2 equations we're going to have no use for, so I'm just going to take these 2 equations here. So the sum of the forces in the x direction for mass 1 and the sum of the forces in the x direction for mass 2. Okay, so let's take them. Okay, so I'm going to rearrange this equation for t, so I'll just add t to both sides and subtract both sides by m2 times a. I'll get this, and then substitute t into this equation, and I get this equation here. And then what I'm going to do is add this term to both sides to get that, and then I'm going to factor out an a from each term to get this. Okay, and then divide both sides by m1 plus m2 to get acceleration. And I'll also need to remember this equation for later on to find tension. Okay, so I'm going to store this equation over here, and I'm going to take this equation and put it over here. So substitute our values in. We knew m1 was 10 kilograms, we knew m2 was 5 kilograms, and we know g for both, and we know M1 plus M2 is going to be 15 kilograms because 10 kilograms plus 5 kilograms will give us 15 kilograms. Okay, so put all that in, put that into my calculator, and then simplify it down, and I get minus 1.4 meters per second squared, and that is our acceleration. And the system moves to the left since acceleration is negative. Okay, so this whole system is going to move to the left, meaning this block is going to go down and this block is going to go up. And that is the answer to part A, and this is the answer to part B. So now we just need to find the tension in the cable. So remember, we saved this equation from earlier on. So all we need to do is just substitute our acceleration into here to find the tension. So if I do that, I'll get this equation here. So all I did was substitute acceleration into there, substitute our values in to get this. Okay, so again, substituted M2 with 5 kilograms. We knew G and we knew the acceleration was minus 1.4 meters per second squared. And that's going to be equal to T. Okay, you just can't see it here for some reason. And then if we solve for T, we get 50.11 newtons. And that is our answer for part C. So that completes part 1. So example 6, part 2. If the system is given an initial speed of 5 meters per second to the right, how far will it move before coming to rest if the inclines are quite long? Take the coefficient of kinetic friction as mu sub k equals 0.2 for both blocks. Okay, so this time we've got friction, so our free body diagram is going to be slightly different. And we know that these two blocks are given an initial speed of 5 meters per second to the right, meaning they're going to move in this direction. So this block's going to be going up, and this block is going to be going down. So just like we did before, draw in our free body diagrams. But this time I've included friction. Okay, so the force of kinetic friction between the block and the incline is going to be F sub F1. Okay, and it's going to act in this direction because remember, friction always opposes motion, because we know this block is going to be going in this direction up the incline in the positive x direction. That means the force of kinetic friction will act in the opposite direction, and we know this block is moving downwards in the positive x direction, meaning the force of kinetic friction F sub F2 for this block is going to oppose its motion in the negative x direction. Okay, so this is the force of kinetic friction between this block and the incline. So for M1, we find the sum of the forces in the x direction, which is going to be minus g times sine 40 degrees, written here, minus F sub F1, which is the force of kinetic friction, and that is in the minus direction, because that's going in the minus x direction, plus T, so T is going to be positive in this case, because this is the force that's driving this particle up, so that's going to be positive, equals M1 times A, and then we find the sum of the forces in the y direction for mass 1, so we've got minus mg times cos 40 plus n1, just like we had before. And then to find the force of kinetic friction, F sub F1, I do the coefficient of kinetic friction times the normal force, where I knew the normal force is going to be m1 times g times cos 40 degrees. I knew that from this equation here. Okay, substitute my values in. So I knew the coefficient of kinetic friction was 0.2. I knew the mass of the block was 10 kilograms, and I know g. So multiply all this together to get the force of kinetic friction between block 1 and the incline as 15.03 newtons. So for mass 2, we do a similar thing again. So the sum of the forces in the x direction is going to be positive m2 times g times sine 61.5 degrees, which we have here, minus F sub F2. So this is in the negative x direction, minus T, okay, because this tension is in the opposite direction, equals m2 times A. So again, the two accelerations, this acceleration and this acceleration, will be the same. And then the sum of the forces in the y direction is going to be minus m2 times g times 61.5 degrees, and that's minus because this force is acting in the negative y direction, plus n2, which is in the positive y direction. So find the force of kinetic friction again, which is going to be the coefficient of kinetic friction, which was 0.2, times m2, which was 5 kilograms, times g, which I know, times cos of 61.5 degrees. Substitute those numbers in, and I get the force of kinetic friction between this block, mass 2, and the incline as 4.68 newtons. So if I substitute this force into here, and then substitute F sub F2 into here, I can then find the acceleration. Okay, so again, these two terms here, so the sum of the forces in the y direction for mass 1 and the sum of the forces in the y direction for mass 2, we can't do that much with, because they don't contain any acceleration and they don't contain any tension terms, so we'll leave them. So after we've made these two substitutions, we'll be left with these two equations. So rearrange this one for t. So add t to both sides and subtract m2 times a from both sides to get t. Substitute that into here to get this expression. So again, I'm going to add this term to this side to get that. Factor out an a from each term to get this. And then substitute my values in to get this. So I knew mass 1, I knew g, I knew mass 2 and g, and I knew m1 plus m2 is going to give me 15 kilograms. Okay, simplify all that down. And then once this is simplified down to minus 39.66 newtons, divide both sides by 15 kilograms to get a, and a is going to be minus 2.64 meters per second squared, and the minus is telling us that the system is slowing down. So now we know acceleration, we can apply our kinematical equations from rectilinear motion to find how far it will travel before coming to rest. So we'll apply a kinematical equation. We're going to use v squared equals v sub 0 squared plus 2as. So we are trying to find s here, substitute our values in. So we know the final velocity is going to be 0 because we're trying to find how long it takes to get to rest. Okay, so the final velocity is 0 meters per second. The initial velocity was 5 meters per second, as given to us by the question. Okay, so the initial velocity was 5 meters per second, and we're squaring that. Okay, so don't get confused and think this is 5 meters per second squared. This is 5 meters per second being squared. And then that minus comes from this minus here, because once we substitute that into there, we get a minus. And then simplify it down by subtracting both sides by 5 meters per second being squared. Okay, the minuses cancel out to leave this. Simplify that down. So 2 times 2.64 is going to give us 5.28. And then divide both sides by 5.28 to get s, where s is going to be 4.73 meters. And that is the answer to this question. So this whole system would travel 4.73 meters before coming to rest. Okay, so if you found this video helpful and you would like to practice some more questions, then click the link on the description, or you can just manually type the website in your search engine or copy and paste the link. So if I just copy the link into here, I'll get taken to this home page. Okay, and if you click courses, engineering dynamics, you'll get taken to the engineering dynamics home page. You've got this formula sheet here which has all the formulas that you need. Okay, so Newton's second law, so these are the equations that we found in this video. And at the bottom we've got trig identities, we've got derivatives, and we've got integrals as well. Okay, so it's all there for you to use. So that's a free formula sheet you can just view on here, or you can download the formula sheet. So if you click onto Newton's second law, you've got this video here that we just watched, okay, and that's free. So anytime you want to watch this, you can just watch it on here ad-free. And you've got this PDF down here with the questions. So you've got questions 7.1, 7.2, 7.3, etc. Okay, so you've got all these questions on here, and you've got the answers at the bottom. So all the answers are down at the bottom here, okay. And you can also download this PDF if you would like to download it. And down at the bottom we have the course content. So all these are just individual videos which completes each individual question on the PDF. So if you'd like to get practice in, you can just start from here.